imagine holding a tiny grain of dust that has crossed the solar system. It may look meaningless, but in the panspermia hypothesis, objects like this are part of a much larger story. Panspermia is the idea that life, or at least the seeds of life, might be spread throughout the universe by natural cosmic messengers, dust, meteoroids, asteroids, comets, and fragments blasted away from planets after major impacts. The word itself comes from ancient Greek roots meaning something like all seed. The basic claim is bold: life on Earth may not have begun here. Instead, life may have developed somewhere else first, survived a journey through space, and eventually arrived on Earth under the right conditions to take hold. That is an important distinction. Panspermia is not mainly a theory about how life began from non-living chemistry. It is a theory about how life might move. In other words, it does not necessarily answer the deepest origin question: how did the first living system appear anywhere? It shifts the question to another location. Maybe life began on Mars, or on another early planet, or around another star entirely, and Earth was later seeded. This is one reason many scientists are skeptical. A theory that says life came from somewhere else still has to explain where that somewhere else was, how life started there, and how it survived the transfer. The most intuitive version is lithopanspermia, which means rock-based transfer. Picture an ancient planet with microbial life near its surface. A huge asteroid impact strikes with enough force to throw pieces of that planet into space. Some of those fragments may contain microbes protected inside cracks, pores, or layers of rock. Over time, the debris travels through space. Some fragments burn up, some drift forever, but a few may eventually collide with another planet. If they survive entry and land somewhere suitable, the microbes inside could, in principle, begin reproducing. The rock acts like both a vehicle and a shield, protecting its passengers from some radiation and extreme conditions. Another version is radiopanspermia, which imagines tiny life forms or spores being pushed through space by radiation pressure from stars. This is a more extreme idea because open space is not gentle. Unprotected organisms face ultraviolet radiation, cosmic rays, vacuum, freezing temperatures, and long stretches without water or nutrients. Still, some bacteria and spores on Earth are famous for being remarkably tough. Certain microorganisms can enter dormant states, tolerate radiation better than humans, and survive harsh environmental stress. Panspermia supporters point to these abilities as reasons the idea cannot be dismissed instantly. The question is not whether space is hostile. It clearly is. The question is whether small life forms could ever survive long enough, in the right shelter, to make the journey meaningful. Comets and asteroids are also central to the discussion because they are natural delivery systems. They move between regions of a planetary system, carry ice and organic material, and have repeatedly struck planets over billions of years. Early Earth was bombarded by space rocks, and those impacts likely delivered water and chemical ingredients. This part is not especially fringe. Scientists already accept that space objects can deliver important materials. The controversial leap is whether they could deliver living organisms, not just chemistry. A comet carrying organic molecules is one thing. A comet carrying viable microbes across vast distances, through radiation and impact heating, is another. That gap is where panspermia becomes much harder to prove. There is also directed panspermia, which sounds like science fiction but has been seriously discussed. In this version, life does not spread accidentally. It is deliberately sent. One form imagines an advanced civilization intentionally launching microbes or biological material to seed other worlds. Another, more practical version concerns human spacecraft. If a probe is not perfectly sterilized, it could carry Earth microorganisms to Mars, icy moons, or other environments. That is why planetary protection rules exist. Space agencies worry about contamination because if we find microbes elsewhere, we need to know whether they are truly alien or whether we accidentally brought them with us. Directed panspermia turns a cosmic hypothesis into a real operational concern. The strongest criticism of panspermia is simple: it is difficult to test. Science depends on evidence, predictions, and experiments that can distinguish one explanation from another. If someone says life came from space billions of years ago, what evidence would prove it? Ancient Earth has recycled much of its crust through geology, erosion, and plate tectonics. The earliest traces of life are already hard to interpret. Finding a microbe-like shape in a meteorite is not enough, because contamination and misinterpretation are serious risks. Over the years, meteorite events have produced speculation, sensational claims, and even hoaxes. That history makes scientists cautious. Extraordinary claims need more than suggestive patterns; they need evidence that survives intense scrutiny. This is why panspermia is often described as a fringe hypothesis. That does not mean every part of it is nonsense. It means mainstream science does not see enough evidence to treat it as the leading explanation for life on Earth. Most origin of life research focuses on chemistry, how simple molecules could form more complex systems, how replication might begin, and how early metabolism in cells could emerge. Panspermia sits beside that work, not as a replacement but as an alternative distribution scenario. It asks whether life, once formed somewhere, could spread. But because it does not solve the first formation problem, many scientists see it as incomplete. It moves the mystery without fully explaining it. Still, panspermia remains interesting because the universe is full of exchange. Planets are not sealed boxes. Impacts eject material. Meteorites from Mars have reached Earth. Dust moves through space. Comets and asteroids cross planetary paths. Even within our own solar system, objects can travel from one world to another over long timescales. If Mars once had liquid water and potentially habitable environments, then material exchange between Mars and Earth becomes scientifically relevant. The question becomes less absurd when framed locally: could early Mars and early Earth have swapped rocks containing hardy microbes? That version is far narrower than life drifting across the entire galaxy, but it is also easier to think about scientifically. A related idea, pseudopanspermia, is much better supported. Despite the similar name, it does not claim that living organisms arrive from space. It claims that many small organic molecules used by life formed in space and were delivered to planets. This is a more conservative and evidence-friendly view. Scientists have found organic compounds in meteorites and in interstellar environments. Space chemistry can produce ingredients that matter for biology, even if those ingredients are not alive. So while full panspermia asks whether life itself traveled, pseudopanspermia asks whether the raw materials of life were partly imported. That distinction matters because one idea is speculative, while the other fits more comfortably with current evidence. The survival problem remains the heart of the debate. For panspermia to work, life has to pass several filters. First, it must be launched from a living world without being destroyed. Second, it must survive space for long enough to reach another destination. Third, it must survive arrival, including atmospheric entry and impact. Fourth, it must land in an environment where it can wake up, reproduce, and compete. Each step may be unlikely. But in a universe with enormous timescales and countless worlds, even low probabilities attract attention. That is why some researchers explore mathematical models of how life might migrate naturally. They are not proving panspermia happened. They are asking whether the physics of transfer makes it impossible, rare, or potentially plausible. So, could life on Earth have come from space? The honest answer is, maybe, but we do not know, and current evidence does not make panspermia the mainstream explanation. Its value is that it expands the way we think about life as a cosmic phenomenon. Earth may be the only known living world, but it is not isolated from the universe around it. Rocks fall from the sky. Chemistry forms in space. Planets exchange material. Spacecraft can carry contamination. Panspermia sits at the edge of science and speculation, asking a provocative question: if life can begin somewhere, can the universe spread it? Until stronger evidence appears, it remains an intriguing possibility, not a settled answer. If you found this helpful, please like this video and subscribe for more explainers.